These are the notes for special cases. The first thing that I need you to do is to cross off the title of the first column, which said types of system. I made this note guide last year, and I'm not happy with that phrase there. So we're crossing that off. Okay? So we're looking at systems of linear equations. There's three possibilities. We could have one solution, no solution, or all reals. Last week we looked at graphing with these three phrases. So the only new thing for today is solving and having a possible special solution when we're looking at substitution and elimination. So in this first box here, it says number of solutions. Well, obviously one solution there is 1. And what's your answer going to look like? It's going to be an ordered pair x comma y. When I'm solving linear equations and I have one solution, graphically that is going to look like two lines intersecting at one point, one intersection. So please go ahead and draw these in, please. Drawing yourself a coordinate plane, sketching two lines intersecting at one point. Again, it's going to be an ordered pair solution. Emphasizing that ordered pair point where they're going to intersect. Now, algebraically, either using substitution or elimination, again, when you have, this is going to happen 99% of the time. You're going to get one ordered pair solution x comma y. Again, the only new thing today is if we were to get no solution or infinitely many with substitution or elimination. So let's look at the next row here. So no solution. No solution means there are 0 ordered pairs that will ever work. You can still use the 0 with a slash through it for your abbreviation. Graphically, you're going to go ahead and sketch yourself a coordinate plane and draw two parallel lines. Because graphically, no solution is going to be two lines that never intersect. And remember, for lines to never intersect, they're going to be parallel. And parallel lines have same slope. In the third column, let's take a look at two equations here that we're looking at with elimination. So it says 3x plus 5y equals 10, negative 3x minus 5y equals 3. So the 3x's, they're ready to eliminate. So if we add them up, but however, not only do the 3x's eliminate, the 5 and the negative 5y, they also eliminate. So on the left side, we're left with 0. And 10 plus 3 is 13. And 0 does not equal 13. So when you're using elimination and both variables cancel out, you're either going to have no solution or infinitely many. Now, most of the time, you're going to see that this is no solution. We'll look at the example next where it shows infinitely many and what that looks like with elimination. That is not too good. All right, third row here. The third row is infinitely many solutions, and we're going to abbreviate that, or you can abbreviate that IMS. Add the word solutions there to the very first column. Infinitely many solutions, we can abbreviate it IMS. Now, graphically, like we saw last week, If I have two equations and I graph both of them and they produce the same line, so I'd have my coordinate plane, I graph my first equation, then I graph my second equation, and when both equations produce the same line, that means infinitely many solutions. All ordered pairs on this line would be valid. They would both work and produce true situations when I plug them back in. Now I changed this problem in the third column a little bit. Again, I have two equations that where my x's are ready to eliminate. If I go ahead and add these two equations up, 3 and negative 3 eliminate for my x terms. 2 and negative 2y are ready to eliminate. And negative 5 plus 5 also result in a 0. So everything eliminates on the left side, and negative 5 and 5 equals 0. This is the only true statement that you'll ever have with elimination is 0 equals 0. Now when you use substitution, you might get 5 equals 5, 2 equals 2, but because of the elimination method, if you're going to get IMS when using elimination, it will always say 0 equals 0. That's the only option. Okay? But like I was just saying, with substitution, you might go through this and get a true statement or a false statement, and we're going to do a couple of these examples below. Okay? So at this time, if you look at the 4 problems below, this is what your homework's going to be tailored to. It's going to be your choice. You're going to look at the problem and decide what's the best method that I should choose. Should I be using elimination or should I be using substitution? For time's sake, I would like you to go ahead and write the answer down for number 1, and that answer is 3, 0. But I don't want you to work the problem out at this time. I just want you to write 3, 0 off to the side and then come back to that and work it out later. Okay? So what I do want you to do right now is to look at 2, 3, and 4, and I'm going to give you about 5 minutes. And I want you to decide what method should I use and approach those, and then we're going to go through your unique answers. Okay? So go ahead and work through 2, 3, and 4. Pick out if I need to use elimination or substitution.
Number 2 should be elimination. Times them to get them to do elimination.
That way.
Number 3 is ready to grab. This one. Yeah. No, that's solution. It's You're not stupid.
All right, we're going to go ahead and start talking about number 2, and then if we need more time, I'll let you go ahead and look at 3 and 4. But on number 2, this is an example where we would use what method? Elimination. We like elimination because the x's are lined up, the y's are lined up. So for most people, they immediately see that 2 and 3, they both go into 6, and that's a pretty easy number to work with. So if we take the whole entire top equation times 3, you're going to get negative 6x plus 12y equals negative 48. We'll take the whole entire bottom equation times 2, and you're going to get positive 6x, negative 12y equals 60. Now when we start to add these up, we notice something very interesting happening. We multiplied by 3 and 2 to get the x's to eliminate, but not only did the x's eliminate, the y's did as well. So negative 6 and 6 canceled, 12 and negative 12 canceled, and we were left with 0 equals 12. And so that is a false statement, and that means there's no solution. There's no ordered pairs in the whole number system that we could ever plug in. There's no x or y we could ever plug in to make both of these equations work together. And if we graph them, what would they look like? They would have been parallel. If we would have graphed them, it would have been parallel. All right, number 3. I included number 3 as an example here because this is a type of problem that we haven't looked at yet, and there's one like this on your homework, where both equations are set equal to y, but graph paper is not necessarily provided on this problem. So when you see a problem like this, y equals 2x plus 1, y equals 3x plus 3, it's ready for you to graph, but we can still use substitution. So I'd like you to put the 2x minus 1 in parentheses and the y in parentheses. We can take this and substitute it in. When you do that, that's an interesting first step. It's a little bit unique compared to the other problems that we've worked out. It says 2x minus 1 equals 3x plus 3. Now, you can probably look at this and notice my variables are not going to cancel out. We're going to be left with an answer, and that answer is negative 4, negative 9. So again, this is another problem that we are not going to spend time working out, but you can go back and finish this problem for practice, and the answer you should get is negative 4, negative 9. Okay? So at this point, we're going to go ahead and look at example number 4. On example number 4, we have that y is by itself, and so what would be the, let me shut the door, what would be the prime example or method, that we'd want to use? Substitution. So we're going to go ahead and use substitution here. Y is that negative 1 half x plus 2 is by itself. We're going to plug that in for the y value. So we're going to rewrite this bottom equation by substituting in. So we have 3x plus 6 times negative 1 half x plus 2, and that equals 12. To finish solving this problem for x, we need to go ahead and distribute. So we're going to have 3x plus 6 times a half. What's half of 6? All right, so we're going to have negative 3x, and 6 times 2 is 12. Now, when we combine like terms, 3 and negative 3 do what? Cancel out, so we're left with 12 equals 12. And so that is a true statement, and that means there's an infinitely many solutions that I could plug in to both x and y and it will always work. Because when I graph both of these lines, what would happen? These two graphs would overlap each other. They'd produce the same line. So again, we have, those are your examples for preparing for special cases using substitution and elimination.